All right. Yeah. Hi, everyone. I'm Viraj. I'm a PhD student at Caltech, and today I'm going to talk about low luminosity 1AX supernovae. So yeah, the speakers before me did a really nice job of setting up the general landscape of thermonuclear supernovae. And just to recap, this is a familiar plot that shows the peak absolute magnitude on the y-axis, and the x-axis shows by how many magnitudes does a supernova decline after it within 15 days of its reaching its maximum brightness. So it's a proxy for how fast it fades. And the type, is there a pointer? Yeah. So type 1a supernovae nicely cluster over here because they obey a relation, and then there's a whole range of other related thermonuclear supernovae that kind of scatter all around in this plot. But today I'm mainly going to focus on the blue points in this diagram, which are the type 1ax supernovae. So 1ax supernovae at maximum light, they are spectroscopically very similar to type 1a's, with the exception that they have low expansion velocities. And in general, type 1x supernovae have a very wide range of expansion velocities from about 2000 to 7000 or even 8000 kilometers per second. And just for context, type 1a supernovae have like higher velocities, typically 10,000 kilometers per second. And then, as you can see from this plot, the 1ax supernovae also have a very wide range of peak brightnesses, ranging from -14 at the low luminosity end to -18 at the high luminosity end. And then they're important because they're thought to be the largest fraction of these peculiar 1A supernovae. The rates of these supernovae are estimated to be as high as about 30% of the type 1A rate. And within 1AX supernovae, there's an interesting sample of events which have very low luminosities of about -14 or so. And there have been 4 well-studied objects that belong to this sample. There are these 4 objects. The prototype of this class is supernova 2008 HA because it was the first object that was discovered. All 4 have absolute magnitudes of about -14. In general, they have low expansion velocities of 3000 to 5000 kilometers per second. They have characteristically low nickel masses, 10 to the -3 solar masses. And because of these low luminosities and low nickel masses, they are considered to be challenges to the 1AX progenitor models. And speaking of progenitor models, because 1AX supernovae are thought to be thermonuclear explosions, naturally there is the debate whether they come from single white dwarfs or the double degenerate channel. And here's a plot that shows the histogram of some of the peak absolute brightnesses of some 1AXs. And as Kate mentioned, the general idea is that the ones at the very bright end, they are most likely accepted to be the outcomes of partial deflagrations in carbon-oxygen white dwarfs. So this is a CO white dwarf that is accreting material from a companion, reaches the Chandrasekhar limit, ignites a flame in the center, ignites a carbon flame in the center, and the carbon flame cannot detonate the white dwarf, but instead the flame shuts off and a small amount of material is ejected that powers the supernova, and a bound remnant is left behind. But the problem with this model is that there have been several simulations of these models, and all of them kind of struggle to explain the low luminosity events. So they all have peak brightnesses that are brighter than -17. There have been some recent newer models which extend it to -16, -15.5. But in general, the idea is that you can't quench the carbon flame soon enough so that you can get a very low nickel mass. So to get around this problem, people have proposed some ideas to explain this the low luminosity population. And one such idea is that they could actually be deflagrations in these hybrid carbon-oxygen neon white dwarfs. This carbon-oxygen neon white dwarfs, the idea is that you have an oxygen neon white dwarf, but for some reason when the white dwarf was forming, the carbon flame did not actually reach the center of the white dwarf, it stopped somewhere. And that's why you end up with a configuration where you have a little bit of carbon left inside in the core of the white dwarf. And so if you have a deflagration, if you have a carbon flame that goes off in such a near Chandrasekhar white dwarf, the model simulations are successful in quenching the flame very quickly, so very little nickel is produced, and then you can sort of produce these very low luminosities of -14 in these events. But the main problem with this is it's not clear whether such white dwarfs should actually exist. Some simulations say they exist. It's a big debate whether there's no actual evidence that these things exist in nature. There's no observational evidence that these things exist in nature. And I said there was a double degenerate model as well, and This model tries to explain these transients as mergers of a carbon-oxygen and an oxygen-neon white dwarf. So this paper by Kashyap et al. 2018, what they did was they simulated this merger of, I think, 1.3 solar mass oxygen-neon white dwarf with a 1.1 solar mass carbon-oxygen white dwarf. What they found is that the CO white dwarf gets disrupted and forms a disk around the oxygen-neon white dwarf. And in the very interior of this disk, you can reach the conditions that can ignite the carbon, and then you get a carbon flame that sort of propagates through the disk and ejects some of the material. That powers a very low luminosity transient. So the transient that they get is an absolute magnitude of -11. And the problem with this model is that there's no observed 1AX supernova that has such a low luminosity. And yeah, so there are these two these two interesting models, but we can't really test them because the sample of 1AX supernovae in this luminosity range is really sparse. And it would be really nice to have a larger sample to study this. But fortunately, we live in the era of time domain surveys. So I personally work with the Zwicky transient facility. I know there's been a lot of mention of the Zwicky transient facility in the context of detecting very interesting and super cool binaries, but we also detect transients. And so with ZTF, we have, for the last 3 years, we have been running the CLUE survey or the Census of the Local Universe experiment. The idea of this experiment is to spectroscopically classify every subluminous transient that happens in the nearby universe within 140 megaparsec. And so far, we have been pretty successful at doing this. We have reached a spectroscopic completeness of 85%. So that really allows us to build samples of populations of transients and study them in detail. Yeah. So last March, we found this very interesting transient 2021 FCG, which was classified as a 1AX supernova eventually. This transient was in the star-forming galaxy at a distance of 27 megaparsecs. So this is one of the nearest 1AX supernovae to be discovered, especially in the last few years. And what was even more surprising is that this transient reached a peak absolute magnitude of -12.5. And that is really low even by 1AX standards. The previous record holder for the lowest luminosity 1AX was about -14. So this is like already 1.5 magnitudes fainter than that one. And this plot shows the multiband light curve. It was kind of faint, so we couldn't get a very, very high cadence light curve of it, but we got like some good data to show that how it declined, and we got some good constraints on the peak explosion time and the peak absolute magnitude. We got 2 follow-up spectra to confirm the spectroscopic classification, and then the spectra of this transient are shown in blue, and then the black spectra show the spectra of the other low luminosity 1AXs, and it's pretty evident that they look almost the same, especially at the same phases. And so some characteristic features in these spectra are these forbidden calcium 2 lines for near infrared calcium triplet, sodium 1D line, and then a bunch of just ion lines and oxygen lines. Yeah, so this pretty much nailed the classification as a 1AX supernova. And this plot shows the bolometric luminosity. Again, we don't have a very good quality light curve, so we can't really place very strong constraints on the luminosity. But it reached a peak luminosity of about 2 times 10 to the 40 ergs per second. And then the comparison objects are shown in gray over here. So this one is already like about 3 times fainter subluminous than the other comparison objects. And the brown dashed line shows the prediction from the CONE deflagration model, and the blue line shows the prediction from the white dwarf merger model. This one kind of lies in the middle, as you expect. If you do some basic light curve modeling, you can estimate the nickel mass to be like 3 to 13 times 10 to the -4 solar masses. Similarly, a very large range for the allowed ejecta masses, that less than about 0.4 solar masses. And then you can compare this to the predictions from the simulations of the deflagration or the white dwarf merger model, and you can see that it kind of agrees with the white dwarf merger model and kind of does not agree with the deflagration model. So maybe there is this object kind of favors the merger model, but it's not certain for sure. And then if you come to these plots again, 21 FCG, it is the lowest luminosity thermonuclear explosion that we have seen. And it kind of lies in between these 2 models. So we really need more explorations or more simulations of these models that delve more into the phase space of these models to see if any of these, this model can be shifted to lower luminosities or whether this can be shifted to higher luminosities. But regardless of where this thing originated in, you expect that there will be Thanks. You expect that there will be a bound remnant left, and such bound remnants were seen previously for example, for 2008 HA. I know Ken and Josiah have some similar models for the remnants. And so we are basically continuing to follow this supernova at late times, and we also have some HST time to look at it at very late phases to see if there is any bound remnant that's left behind. But in the last 2.5 minutes that I have, I want to talk about a work in progress, which is now that we found this extremely low luminosity event and we have this 4 years worth of data from the CLUE experiment, we wanted to go back and see are there more events like this in the CLUE sample. And we did that, and we found 4 more events, so this one and then 4 more. And the absolute magnitudes of them range from -12.5 to -16. And then once you have data that spans this large range, you can do stuff like you can try to build a luminosity function for these events, which corresponds, and if you do that, it corresponds roughly to dn by dl approximately L to the -2.4. So you can see that this is a very steeply increasing luminosity function. So you expect to have many more of the events that are low luminosity compared to the ones that are at higher luminosities. And once with using the luminosity function, and what you can do is try to measure the volumetric rate. So briefly, the way this process works is you construct a template light curve for 1AX supernovae using the sample that you observe. You use the luminosity function to simulate fake transients in the universe for a range of rates. And then you use the ZTF pointing history plus the selection criteria of CLUE to see for every rate how many of these 1AXs would you actually have detected in your experiment. And you can make plots like this, which show the number of events detected versus rate. And basically you saw 5 events, so you can get a rate estimate of this. And the results of this are kind of shown in this plot, which shows the rate in per megaparsec cube per year as a function of the peak magnitude. And one thing that's very interesting over here is that the rate is really, really high. It's almost like a few tens of % of the local 1A rate. And the rate increases very steeply to lower luminosities. And now the question is, we have these 2 models, the deflagration model versus the white dwarf merger model. What do binary population synthesis say about the rates? And so if I put the population synthesis rates from these 2 papers, so for the carbon oxygen neon white dwarf is shown in gray, and the white dwarf merger is in the red, and both of them kind of agree with the expected rates, except maybe at lower luminosity. So it's unclear how low this luminosity function actually extends. So if it does extend to really low luminosities, then we may need both channels to contribute towards this. Yeah, and I'll leave the summary on. This is a really interesting class of transients that we don't really understand, and we are now in a position to find out more about this. And yeah, happy to answer any questions.
Questions, Boris? This is Boris. Do you have any estimates for the chemical composition of the bound remnant that is left behind?
Not currently. There are estimates that each of these models have. They provide a list of the fallback material. They provide an estimate of how much material falls back and the composition. But we hope our future observations can help us kind of understand that. Yeah.
So this may be related to Boris's question. Have you thought, I know there's not a lot of modeling, but have you thought at all about relating these to oxygen neon deflagration models as opposed to the hybrid carbon oxygen neon deflagration models?
I haven't looked at it in a lot of detail, but I thought my understanding was it's difficult to get these deflagrations in oxygen neon white dwarfs. But maybe someone can correct me if I'm wrong. Okay.
I think it's still uncertain.
Okay.
Can you say a little bit about what's the neighborhood of this object, the one you've got? You said it's in a spiral, but it's really close. So what's going on in the neighborhood?
There is no archival HST imaging, so we don't really know what's going on in the neighborhood. In all of the deep images that we have taken, we don't see any excess, like, I don't know, some people say that, oh, are there any dwarf galaxies or something going on over there, but we don't see any signs for that. We're waiting for the HST data to come in a few months.
Could you just go back to one of the images that showed the galaxy? You don't have oh, there's a scale, sorry, okay. Yeah, okay, thank you.
Yeah, this is Ivo Seitenthal again. Thanks for your great talk. And just because you asked, so I was involved in the 2015 Chromer work, and basically what we've done there is we were looking for models for 2008 HA, and what we noticed is just igniting CO white dwarfs with deflagrations. You know, we like the whole in the remnant that they're faint, but we couldn't get them faint enough. And so then a class of models came out from, you know, Pavel Denisenkov and I think Chen, and they basically had some evolution of super AGB stars where the inward moving carbon burning flame was quenched and shut off, and you're left with a core that stayed, you know, stable and not mixed of carbon oxygen. And so then the idea was, okay, we can still accrete that to Chandrasekhar mass, ignite the flame, and when that hits the oxygen neon, the flame plausibly extinguishes, and even that's not clear, maybe it just keeps burning. We just extinguished it, and I think the idea is that if you have an oxygen neon white dwarf, it's not completely clear what happens. The normal understanding is that, you know, you may or may not collapse. I mean, there's the simulations by Sam Jones, for example, right? It's quite, it's not completely clear what happens, and it depends on things like convective Urca process. It's quite uncertain, and maybe something to look into actually. Yes.
Yeah, that would be very interesting.
But you know, I guess my point was what made it faint for us is that we had a plausibility argument why the flame would extinguish. So having that interface, you run into it and it goes out. If you ignite, once you ignite the oxygen neon flame, if you say it does ignite, then it will just burn too.
Yeah.
It probably won't be as faint.
Can you go back to the histogram of absolute magnitudes? So there are a bunch at, I don't know, -17 or minus 18 maybe. Obviously they're brighter, right? And so they're just easier to see.
Yeah.
But does that jibe with the luminosity function that you have? Like if you extend the luminosity function past where you stopped it?
So there are, in the volume limited survey, there are not that many of those because as you saw, the luminosity function goes down. And I tried doing that. I wish I had a plot of that, but there is, I think, some indication that the luminosity function it may be slightly different luminosity function at those very high luminosities, but I don't think it's statistically significant at this point. It's really, really small number of events. So the error bars are really high.
Anyone else? Last chance. All right, let's thank him again.